Welcome to Breadboarding. In the previous video in the PLD mini-series, so Programmable Logic Devices, we covered a complex programmable logic device, the ATF1504 in the 100-pin version, and I covered actually how to solder this onto a 100-pin breadboard adapter, and I did some basic testing of it. In this video I'm going to be covering my experience to that and actually looking at using a slightly larger chip, the ATF1508, and what some of the reasons for that is. So this is part 9 of the Complex Programmable Logic Devices CPLD series, and this is really just covering tips and some of the things I've discovered in using the ATF1508, which is a 100-pin chip similar to what we used in the previous video, only this chip has 128 macro cells, not 64 as the 1504 has. So let's take a look at the board where I'm using this. So this is actually the CGA video card that I'm building at the moment, but obviously this is one of the first projects where I'm using one of these CPLDs here, and so I thought I'd record this video just so that I can program it with some of my test scenarios before I end up configuring it for the video card. So this is similar to what we did in the previous video. The only difference really now is that the JTAG connector down here is down here. There's also the 44-pin complex PLD down here that I was going to be using this project as well. You can see over here to the right hand side here, this is the Atmel programmer, in-circuit, in-system programmer, and connected with the JTAG connector over here. And over here I've got my logic analyzer, and I'm really just using this to provide a couple of oscillator inputs here for providing the test signals. And what I'm going to be doing is showing you some oscilloscope traces from the oscilloscope probe here and covering some of the problems I ran into, and those in turn has been converted into tips to hopefully save you some of the pain. So let's take a look at the PLD configuration file that I was working on for the CGA video card project. Now this is quite a complicated file. I'm going to be covering the contents of this in more detail in the CGA video series, but I just wanted to actually show you this to give you an idea of how complex these things could be. So this PLD here actually combines probably about 6 or 7 PLDs from the original project, and you'll see here I've got the layout here. So some of the signals we'll be looking at to the P0 to P4, the video outputs to the video DAC, and we've got things like the horizontal sync, vertical sync, display enable, various CGA chip enables, D0 to D7 inputs here, and we've also got the video data 0 to 7 here. So there's quite a few inputs in here and lots of latches and various other things. And what I did is try to assign the pins to suit the breadboard layout to actually make the wiring up on the breadboard as simple as possible. Now in the early stages, what I also did is where we have internal registers and things, so this is where there isn't an external I/O pin, but we can use a pin node to actually have a register. So for example, the video data, and the pin nodes needed for the blink clocks for the character and the cursor, which are derived from the vertical sync, and also the color register values. These are all things which are only needed internally and so can use pin nodes. Now originally what I did is I assigned all of these a specific number, but as I'll explain, you can run into problems then by manually assigning these and not giving the fitter the flexibility to move them around a bit to get things to fit. And probably the bit that was most complicated is down the bottom here. You'll see there's a lot of rules in here, but these rules here for the color output into the video DAC were combining multiple rules from higher up as well. So we have the intensity red, green, blue values there, and this is also combining all of these things. Now the problem that I ran into is when you then compile these in WinCUPL and it runs the fitter, this is the actual output that I ended up with. And I ended up having to go backwards and forwards quite a few times because it ran out of space in some of the blocks. If we just have a quick look at the data sheet to explain what the blocks are, I mean, it wasn't something I was aware of before I did this. So this is the data sheet for the 1504, and you can see here that the 100 lead has 64 user I/O pins, although 4 of those are used for the JTAG programming. If you go up to the top here and we look at the high-level diagrams, we can see that there are groups of macro cells in groups of 16, and these will be known as blocks. And then this particular chip has 4 blocks, A, B, C, and D. And there are some limitations on what you can do with the A, B, C, and D, and you can run into certain limits. So when we talk about this, this is where it actually comes from. And one of the big differences between this chip and the 1508 is that the 1508 has 128 macro cells and actually has 8 blocks, so it's a bit more flexible. So when I managed to get the fitter working, it actually comes up with quite a few warnings. So I'm using more than 90% of the logic resources. Atmel recommends using a larger device. So you get quite a few warnings and things here. Although there aren't any failures, there are sort of a number of warnings here. And what you'll see as we go through, this is attempting to place floating signals. Now all the physical I/O pins have been expressly identified, and because we have pre-assigned keep property here, then it should mean that the fitter doesn't try and move any of the ones that we've dedicated to a specific pin. But that does mean then that there's a bit more trouble moving things around should you have a design that doesn't fit. So going through the output here, you can see that it does produce the diagram for you, although there will be a few gaps where perhaps it's had problems fitting things in, but generally you'll see that the output here pretty much matches the diagram that we had in the PLD there. But where you then have to start paying attention is the fan-in for block A. So you can see there's 40 items coming in the fan-in there, and a number of them, you'll see down the bottom here, this XXL, 2110, 214, etc. These are internal terms that have been generated because of the complexity of some of the rules, and this is where I was falling foul of the scale of this particular PLD. So although the inputs and outputs were okay, and theoretically the number of macro cells I needed was sufficient, when we ended up with these internal terms here, then this is what actually caused me to run into problems. And you can then see that the assignment of each multiplexer block is actually in here as well. So if you use the fitter to do everything automatically, you don't care about which pins are connected to which, then the fitter will actually shuffle all this stuff around for you and actually get it to fit as well as possible. And on a printed circuit board, that probably doesn't matter too much because the layout is probably a bit more flexible. But when we're dealing with breadboards, we want to keep the similar pins together, so it makes wiring things up a little bit easier. So you get all these blocks, and then there's the rules themselves, and you'll see when we get down here, the rules for these sort of terms here, which are internal terms because of the complexity of the rules. This is what actually blew things up when I was actually trying to get this working. Then we've got the assignment of the pins, so this should be pretty much as we had assigned them. And you'll see here that the pin nodes have been assigned automatically, and the reason for this is that there's no need really to assign specific pin node numbers, and I'll explain in a minute that if we leave this for the fitter, then it will just try and squeeze things in the way that actually fits the best, hence the name of the fitter. And then this table here becomes a little more interesting because it includes a lot more information, particularly where we're using registers and reset and all the other things. Then we can actually see a lot of these things in this column here that shows us what our register type is, what clock is, and these clock enable and reset and preset, etc. Then down the bottom, this is the bit that probably makes it a little bit more obvious. What we can see here for our logic array block A, B, C, D, and you can see these are for the macro cells 1 to 16 all the way up to 49 to 64. And you can see that we're using 16 out of 16. We're using quite a lot of the I/O pins, not all of them, but enough of them. And really that when we look at the logic cells used and some of the nodes and the feedback macro cells and things, everything's got quite busy and quite full. So what I decided to do is, rather than spend any more time trying to squeeze things into the 1504, I thought I'll order some 1508s and see how I get on with those. So let's just take a look at the 1508. The 1508 is in fact already installed in here. This is the 1504, so they're identical really from the outside. The only difference really being is that 1504 has quite a lot of not connected pins, so where the white is on the I/O connector there is basically where those are pins that shouldn't be connected, just so I didn't accidentally wire them up. So soldering this chip was exactly the same as I did in the previous video. It's a bit fiddly, but with a lot of flux and things, then I've been able to get this in and working. And what I've done to test this is I've modified the default sort of PLD files that I had in the previous videos. So this is an ATF1508 AS 100 pin, and all I've done is I've updated this to include all the correct macrocell numbers, and you'll see now that the macrocells are going up into the 100 and up to 128 now. I've now also organised the macrocells into these groups. Just makes it a bit easier for you to see how if you run out of resources within each group, it just makes it a little bit easier to actually see what's going on. And I've done a similar thing to what I did before, but rather than using all of the gates, what I've actually done is just use the A and B inputs, the exclusive OR and the exclusive NOR. And apart from a couple of clock terms and things for the first couple of macro cells, what I've done is across all of the other macro cells going from 8 all the way down to 128, you'll notice that where there are macro cells which are not connected to the outside world, then I haven't included those. But what this just means is that I've got a test here that if I go around all of the external pins, I should be able to see the output on these pins that will show some sort of waveform on the basis of what the input A and B are for the exclusive OR and the exclusive NOR. So I'm just going to compile this. The window there is the fitter running in the background. We just check to see we've got all the files. You can see we've got our fit file and we've also got the JED file that's been produced. Just have a look at the fit file. So when you open a fit file, it's always worthwhile going down the bottom first, end fitter, device fit. So this means that it should have produced the JED file and that everything has worked out okay. And we can see here that we've got all of the I/O pins actually have a pin assigned here. We've also got the global pins are also defined there. And you'll see here that all of these pins have actually got the exclusive OR or exclusive NOR conditions on all of these I/O pins. All we need to do is to put some sort of signal on the pin 8 and pin 6, which are the A and B inputs. So if we put a signal on there, then we should then be able to check the output on all of the pins. We just need to program it and switch on the power. Just scan the cable. So this is the version 1 test. Now what I have found is that I've needed to sometimes erase the chip specifically through the menu here. So in fact, although I've got the programming command there, what I'm going to do in fact is to load the arrays first of all. You'll see here this is a dedicated arrays. What I was finding is that there are a couple of pins that weren't being programmed properly. So when I was going around testing each of the pins, I found that pin 99 and pin 100 were not being programmed correctly. And when I erased the chip properly and then loaded the test here, we'll just now program this. You see here we've actually got our ATF1508 version 1 JED file. Okay, so that's finished. So we're just going to make sure we've got some test signals in here. So I'm using the logic analyzer frequency generator settings here. So I'm just sending out 20 kilohertz. One's got a slightly different duty cycle. That just means that we should actually get a more interesting waveform. And I've also got the oscilloscope probe wired up so I can actually test various parts. So if we just have a look at the 2 clock signals there. That is the first clock signal. And this is a second clock signal. We can see the different duty cycle. And that should mean that when we then look at another pin, so if I look at one of the I/O pins here, you'll see that we get a different signal. If I go to another pin, then this is actually the inverted version of that. So basically what I've done is gone over every single pin and checked to see that we actually get this type of signal. What that basically meant is I was able to detect where I had problems, and in particular where I had problems with pin 99 and pin 100. If I just check those now, just to check that those are actually working okay. In fact, those are connected to a 25 megahertz clock. So this, you can see here that in fact these two pins are actually connected to the 25 megahertz dot clock that I'm testing for the CGA card, and we've actually got 6 megahertz coming off that pin, and if I go on to the other pin, that should be about 12.5 megahertz. Now we have 12.5 megahertz. So in testing this is how I was able to determine where these particular issues had. I also have run into certain problems. If I didn't have the ground and 5-volt lines connected properly, you'd get some weird output on some of the pins. So if the power wasn't connected for some of the I/O pins, quite understandably the outputs on some of those pins was a bit erratic. So this is the programmer that I was using. This is the Atmel programmer. I happened to get one from eBay that came without the case, but was about a third of the price. This program was out of stock at a number of suppliers, including Atmel. Should be available now, I believe. This is a JTAG header output. Now, if you're using the developer kit, I'm not sure it has adapter for 100 pin, but it's easy enough to wire up on the breadboard. We're using one of these adapters, and in fact, the 1504 and the 1508 have the same output pins, so it didn't require any changes there. So here are the tips. So I wasn't really aware of the 1508 at the time when I ordered it. I just looked at the 1504. Now, I've ended up ordering a 7 nanosecond 100 pin TQFP chip. This has 128 macro cells and 80 I/O pins, although 4 of those are dedicated to the JTAG in-system programming. It was a little bit more expensive, but it has actually saved quite a lot of time. Now, the 1504 10 nanosecond part is slightly slower, but the speed shouldn't be significant between these two. When looking on Mouser, there were quite a lot of difference in price between the various speed ratings. But the 7 nanoseconds seem to have the sweet spot for nice and fast, but without being too expensive. So as I've shown, the complex rules resulted in more internal terms, and we ran out of macro cell fan-in by block. So you had to start reorganizing things according to these blocks A, B, C, and D, which I've shown you. So I managed to just get it to fit in the 64 macro cell version, but as I said, the fitter was advising to use a larger CPLD, and I also needed to make sure that all the ground and all of the VCC pins were all connected properly. So the other issues I had, so in the previous video I covered that when I was having some problems getting the pin keep off property to be set properly, if I shortened the path to the PLD file, then it appeared to work. So if you do have problems getting the fitter to actually understand some of the settings you're sending it, try shortening the file paths and see if that works. Don't assign the internal pin nodes to specific macro cells. So originally I'd be assigning, say, pin node 602 to test macro cell, but in fact, if you just let the fitter do this, because the pin nodes, it doesn't really matter which one's connected to where, and the fitter will actually reorganize the various pin nodes so that it'll actually fit optimally, particularly within the various blocks A, B, C, D. So these are the properties that I have included in all of my files, and there's various other resources on the internet which advise using these as well. So if I do assign a pin number to a macro cell, then I don't want the fitter to change it. Occasionally you do end up then having to shuffle things around if you do run out of resources, but I think with the 128 macro cell version that shouldn't be an issue. Disabling the pin keeper, that enabled the logic analyzer to be able to see what the voltage is on the outputs. With the pin keeper on, then the logic analyzer was struggling to see some of the output values and things. I've enabled fast output on, so this means because we're using it for video, it's actually got a faster slew rate for the output pins. And also it's advisable to put the JTAG equals on. What that does is prevents the WinC UPL and the fitter from disabling the JTAG in system programming. if you were to use some of the macro cells used for JTAG by mistake, you could actually end up disabling the ISP programming. Now, in the comment in the file, there is actually, I think if you apply 12 volts to the output enable, then you can re-enable JTAG programming, but it's best not to do that. One other strange thing I found is that the fitter doesn't like legal CUPL variable names. So I had some variable names derived from the original CGA video card 640BW, which was one of the control register outputs. And I had to change those from 640BW to BW640 because the fitter didn't seem to like to have the numbers at the beginning. And I also said what was confusing for quite a long time is trying to work out why my pin 100 and pin 99 didn't get programmed properly. And quite often, because it's on the top corner of the CPLD, it tends to be one of the ones you might tend to use. So by erasing the CPLD specifically as a dedicated instruction and then programming it, then this seemed to fix that. Now, theoretically, the programming the JED file erases the chip first, but for some reason it didn't work properly. So now I'm hopefully in a pretty good shape to carry on with the Breadboard PC CGA video card. Now, one of the things I have sort of already recorded in building this out, I'm still in the process of recording this video and finalising it. I was going to be using this additional PLD down here, but in fact I think now that what I'm going to be able to do is actually combine all of that functionality into here, and we also should be able to get rid of the 74LS 646 buffer chip here. So hopefully when you get to see the CGA video card video next, this chip and this chip will have also then disappeared into here if I manage to get it all working. And so hopefully it should make this whole thing a bit easier to wire up. The programming of this chip is going to be quite complicated. If you want to see that video, have a look at the links at the end of this video for the Breadboard PC playlist. And if you don't want to miss out on future videos, then please hit subscribe. And if you could hit like for the video, just helps to make these videos available to more people. Thanks for watching.